Right.
All right, so today we'll continue with our discussion about limits. We are now in section 1.4 in the slides. So we have a lot of very interesting concepts to get through today. And so this section 1.4 is going to discuss continuity and one-sided limits. So they're going to start out by informally telling us how to determine if a function is continuous, at least at a single point. Later on, we'll see how to determine if it's continuous over an interval. Right now, we're focused our attention on a single point. And basically, in a nutshell, all you have to do is make sure that there isn't a gap in the curve that you're looking at. So in other words, if I have something like this, say we'll use f of x equals x squared. No matter what point I pick, let's say I'll pick 2, you can see the value of the function is on that curve, and there is no hole in the curve, there's no gap, there's nothing, there's no breaks in the curve. So we say here that this function is continuous, x equals 2. In other words, I've actually had this described to me as if you can draw this curve with your marker or your pen or whatever without taking it off the paper, then it's continuous. Okay, so in other words, it's a curve, it's a smooth continuous curve. There's no interruption in it, there's no gaps. But if instead you had something like this, that's a different matter altogether, because at this point, let's say x equals 1, obviously there's a discontinuity, although there's only one. Now, there can be discontinuities at different points, different values of x, or there can only be one, or there can be none at all. There's a lot of possibilities, but here it should be clear just by looking at the graph that f of x is discontinuous at x equals 1. Now, there are formal ways of proving continuity and discontinuity, but just looking at a graph, it should be clear just by looking at it if it's continuous or discontinuous at a single point. Now, here they got some examples for us. Let's take a quick look. So in the far left, you can see there's a hole. F of c is undefined. Okay. Just like the one I have up here in the top. And therefore, this one is not continuous. In the middle, you can see there's a gap, and the function jumps directly from here to here. And so again, we have a discontinuity. And in addition, now when this kind of thing happens, the limit itself, as x approaches c, does not exist. Okay. Here, the limit actually does exist, whatever this point is. Let's say this is 3. In this case, the limit as x approaches c is actually 3. Okay. But here, because of this jump, the limit does not exist. And of course, the function is not continuous at x equals c. Now, in the last case, this is an interesting case. We got a hole, but we also have a value down here. So in other words, here, f of c is this number, whatever it is. The only problem is the limit, as we're getting close to c. Now, this is the limit right here, whatever that number is. F of C is this one. So you can see there's two different numbers here. And that indicates that the function is discontinuous or not continuous at x equals C. Okay, so in other words, there's different ways in which a function can be discontinuous. This is the formal definition. Continuity can be destroyed, or there can be no continuity at x equals C. If the function is undefined at C, that's the first case. F of the limit does not exist at that point, which is what's happening in the middle case. And in the third case, the limit exists, but it's not equal to f of C. So for any other case, the function is continuous, right? So if none of these conditions are true of your function at point C, then the function is said to be continuous at x equals C. But intuitively, it simply means it's just imagine you can draw the curve and there aren't any breaks in it. Now, they're going to extend this to being continuous over an entire interval. Okay, so basically, what they're saying here is that if you have a function defined over some interval a to b, so over the open interval a to b, which means it does not include either endpoint, if we can show that the function is continuous at every individual point, then the function is continuous here over the open interval AB rather. Okay. Now you can tell again just by looking at it. Now it matters actually when we look at these formal definitions, it's very important to keep an eye on whether or not the interval is open or closed, because the way it's written here, they're allowing for the possibility that there could be discontinuities at A or B themselves. Okay, like you can have something like this. So this function is also continuous over the interval, the open interval. And so just as a quick reminder, the word open indicates that neither A nor B is in this interval. Okay, so in other words, if you remember, let's say we look at the real number line. This interval would be represented as B with square brackets because both intervals or both endpoints are included. Okay, then at the other extreme, we would have this. So in other words, neither is included. This one is closed. This one is open. And then there's two ways in which it can be half open. Now, these, you can write this in a few different ways. You can write semi-open, semi-closed. The point of it is that one of the endpoints is included and the other is not. All right, so those are the only four possibilities we might encounter for an interval. In the first case, both endpoints are included, so we have square brackets and it's said to be closed. In the second case, neither endpoint is included, so we have round brackets. So we call that an open interval. And then in cases 3 and 4, one of them is open. So we have a square bracket for the one that is, a round for the one that's not, and we can think of that as semi-closed. Okay. So anyway, I just want to make sure we remember how that works. So in this case, you can see that it's continuous between A and B, but not at either A or B themselves. So we say that f of x is continuous over the open interval a to b. Now, oh, by the way, if the function is continuous on the entire real number line, like the first case we had, f of x equals x squared, since it's a polynomial, there are no gaps or breaks in this curve. And so it's going to be continuous for the entire real number line with no exceptions. And this is often referred to as either everywhere continuous. Depends on the textbook. Some books call it continuous everywhere. That's the one I'm used to seeing. And so that's what you're going to find with polynomials, at least. All right. Now, there are two basic types of discontinuities, as we've started to discuss, removable and non-removable. So here's the classic examples of that. So clearly, in both cases, we have a discontinuity, but here, what they're doing is saying, well, all right, here's your function. We know that there's a discontinuity at some point C. So if we define a value here, whatever it is, we think of that as removing the discontinuity. So in other words, this way there's a value associated with x everywhere in that interval. The case where the curve splits apart is the one where there's what we call a non-removable discontinuity. This one, yes, you can see the gap. And it matters in some senses that, like, for example, limits, we know for a fact this one doesn't. It'll also affect other types of procedures we'll carry out in calculus, but it's important to understand if there is a discontinuity, which type it is. So we may be able to do something about it, basically. Now, here's an interesting case. F of x equals 1 over x, the so-called inverse function. Now, in this case, it's pretty clear that there is an asymptote since x equals 0 leads to division by 0. The line x equals 0, which is just the y-axis, is an asymptote of f of x. So in other words, any value that when plugged into a function like this leads to division by 0, any value of x that is going to lead to a vertical asymptote. Okay, so that's what we have here. Now, in this case, the domain of this function is all the real numbers except for 0 itself. Right? So as far as continuity is concerned, we would say that this is by the way, this is non-removable discontinuity, but we can say then that the function is continuous everywhere in its domain. Okay, in other words, the domain does not include the x equals 0. So the function is continuous everywhere in its domain. Ah, you see, so in other words, that asymptote is not part of the domain. So therefore, when we say that the function is continuous over the entire domain, we're excluding the x equals 0. The rest of the curve, as you can see, is continuous. So in this case, the function is continuous everywhere in its own domain. Now, here's an interesting one. We can see that you have a problem with division by 0. Okay, so why don't we go to Symbol Lab and see how it reacts to this? All right, so let's see what that graph looks like. All right, well, this is what they have. I mean, you can see it's a line. It's a straight line. It's a linear function, except for that little hole there. And this is going to happen where x equals 1. Because if you allow x to equal 1, then you're going to have division by 0. Now, of course, you'll recognize that if you reduce this algebraically, so it's basically the straight line. This function is g of x means it's the same thing except for that hole. Okay, so you might remember too. So if I were to plug 1 into this f of x, sorry, g of x, f of x right here, I'll have 2. So you remember from a previous section that the limit of g of x does exist, and in fact is equal to 2. Because of the fact that these two functions are identical everywhere except at that point, x equals 1. So therefore, the limit of g of x is the same as the limit of f of x when x approaches 1, and that in turn is equal to 2. So g of x has a removable discontinuity. And in spite of that, it still has a limit. Okay. Now, at the same time, though, the domain of g of x is all reals except for 1. So since 1 is not part of the domain, then we can say that g of x is continuous not everywhere, but within its own domain. So far, so good. All right, let's keep going. Now, this is one of those bizarre functions where it's almost like you've got two functions that are glued together. You can see the behavior of this thing is very bizarre. we said that this is said to be a piecewise function. And so in other words, it's defined over different intervals. As long as x is non-negative, this function is a linear function, x plus 1. And then once we hit the positive numbers, it becomes a quadratic function. And this is really neat. Okay. So this one, in spite of its bizarre appearance, is continuous everywhere. It says here continuous on the entire real number line, which is the same thing as saying continuous everywhere. There are no discontinuities. It's a strange function, but it's continuous everywhere. Now, here's the sine the sine curve. You can see how it behaves. It's a curve that continues to repeat itself over and over. And so you can see that no matter where x is, there will never be any discontinuities in this function. So we can say that it is also continuous everywhere or over the domain, which is the same thing in this case because the domain is the entire real number line. All right, now we're going to introduce the concepts of limits, one-sided limits, meaning you can calculate a limit focusing only on values that are coming from the right, so to speak, and coming from the left. In other words, here is what we mean by a limit from the right. So in other words, we're looking at the behavior of this function as x approaches c from the larger values from the right of the real number line. And so here you would write this as the limit as x approaches c with a little plus sign. And of course, you can probably imagine what the other one would be. Here, we're considering only x as they approach from smaller values. So here we would write this as the limit. X goes to c with a little negative approaches, or this is the limit as it approaches x, f of x, or sorry, x approaches from the left. Now, what's interesting is that if these equal each other, then our limit exists. You just simply write it as c. We don't put plus or minus because it's understood that it is the same from both directions. If these are different from each other, this limit does not exist. Okay, so that means that can result when you have a function which is discontinuous, but with a non-removable discontinuity. In other words, this type of thing right here, this is when you're going to run into that. So in other words, if you had this case, let's say this is 8, and this is 4. So coming from the left, we're converging to 8. Coming from the right, we're approaching 4. The two are different from each other. And that implies that the limit as x approaches to c does not exist. They mentioned that before anyway. If you come back up here, you'll see that. Here we go. No, actually, no, it was before that, I think. Here we go. That's the case in the middle. Okay. In other words, what we're seeing here is the reason why this limit does not exist, because the limit approaching from the left and from the right are different from each other. Therefore, this limit does not exist at x equals c. All right. Now, in a case like this, now here's an interesting example. We have f of x equals radical 4 minus x. So they very kindly gave us the graph. Anything outside that range of x's will give us an imaginary number. So the domain here is restricted to being between negative and positive 2, including both of those numbers. But you can see from the graph over that interval, the function is continuous throughout the entire domain. And we might be interested in taking the limit. We're going to approach x minus 2 from the right. Oh, sorry. It's minus 2 from the right. We have to be careful with our notation. So in a case like this, we can just solve with direct substitution. All set. And this is what I've already mentioned just a few minutes ago. If the limit approaching c from the left and the right are equal to each other, then the limit exists, and it is equal to the same number L. All right, so we've already seen this. By the way, if you notice, it says if and only if. That means that the implication goes both ways. So in other words, in terms of logic, we can make two equivalent statements. So if x, limit x approaches c from the left, but we could also write it like this. Okay. So in other words, one statement implies the other and vice versa, so to speak. So in other words, the implication goes both ways, if and only if. In terms of symbols, you run into this sometimes, and you'll probably see more of this and get further and further into math. Um, So in the first case, that pointy arrow symbol means A implies B. Then in the second case, B implies A. In the third case, A implies B and B implies A. So in other words, you could think of this as a compound statement. And so this is what we mean by, this can be also written as A if and only if. Whereas this one can be written as A, B if A. And this one means A if B. All right, I just want to throw that in there so you can see what that's supposed to represent, what that wording is actually telling us. Now, with a closed interval, in order to be continuous on a closed interval, as opposed to an open interval. Remember before, with the open interval, we don't have to worry about the endpoints, but here we do. So in other words, to be continuous over the entire closed interval, we need to allow for it to be continuous over, let's say, A to B. But we also need to know that the limit as x approaches A from the right is f of A. And in addition to that, the limit of f of x as x approaches B from the left has to be f. I should have worked this in here. Has to be f of B. Okay. So in other words, you can't have any strange behavior at the endpoints. Like if you had something like this instead, something bizarre like that, well, then the function will be continuous over the open interval, but not the closed interval. Okay. There's certainly a discontinuity at f of A. All right. So that's the formal definition. Now here we've got, that's the graph, square root of 1 minus x squared. And this is the graph. So they want to know the limits of the two endpoints. So the limit of x as x approaches -1 from the right equals 0. Oops. And the limit as x approaches +1 from the left is also 0. And of course, you can see just by looking at it, the function is continuous over the open interval. So that just tells us that the function is continuous over the entire closed interval. Okay. Now, what are some of the consequences of continuity? Well, if I have two functions that are continuous, f and g, at least at the point x equals c, then what you can do, if you were to, now b is a real number. If I multiply b times f, this is also continuous at x equals c. F plus g is continuous at c, f minus g, f times g, and the quotient as long as we don't have division by 0. So that could come in very handy, depending on what you're trying to accomplish. So, okay, what do we have here? I mean, these are just illustrations of these properties. Like if your function was this, let's say f of x is x, this is g of x. So just to use that as an example, what they're basically saying is that if you have two continuous functions like these are, if you add them together, the result will also be continuous. That's all they're saying. Now, it turns out, now here's a fun result, because everybody loves composite functions, I think. If g is continuous at c, and so is f, f is continuous at g of c, then the composite function, f of g of c, x rather, is also continuous at c. Now, by the way, I just want to, here, they've thrown in this example. You probably have seen graphs of the tangent before. The tangent is a very strange function. Remember, the tangent is equal to the sine of the cosine. And when the cosine is, just double check this. Cosine of 90 is 0. Okay. So that means then that every time we have not just 90, but which by the way, 90 degrees is pi over 2. You then go on to, so in other words, if this is pi over 2, the tangent will have an asymptote here. It looks something like that. But then because it's a cyclical function that repeats itself every time there's another pi, that means that we're going to have the same problem at 3 pi over 2. The cosine of 270 is also 0. And so at that point, the tangent would also have an asymptote. So in other words, every 180 degrees or every 2 pi radians, we're going to have the same thing. So in other words, the tangent is only continuous everywhere except at those points, 90, 270, 450, et cetera, et cetera. So it's going to be continuous over all these open intervals, but not over the entire real number line. It'll have multiple discontinuities. Now here they look at this function, sine 1 over x. Um, yeah, look at that thing. Well, the problem here is that it's undefined when x equals 0. So they've sneaked this in here, 0 when x equals 0. So in other words, this function is continuous everywhere except at 0. All right. Now, the intermediate value theorem. This is one of those results that by itself, I'm not sure what you're going to do with it, but you can use it sometimes to help you find the existence of a solution. So what it really is saying is, listen, if you've got a closed interval with a continuous function, let me just copy this so you can see it better. Though I must say that it has several useful implications. Sometimes these terms seem like by themselves, they're like, well, they're interesting, but what are we supposed to do with this result? But it turns out there's often many different important implications of it that are hard to see until you start to need them. What it's telling us is that whatever this function is, as long as it's continuous over this closed interval, here's some k. These are the endpoints. This is f of a. This is the value of the function at the left endpoint. This is f of b. That is the value of the function at the right endpoint. K is somewhere in between. And what this is saying is that no matter what k is, as long as it's in between these two, there's got to be some c in this interval such that f of c2 is k. Okay, because the function is continuous, there's no gaps. So therefore, no matter how bizarre this function is, as long as I pick a value in between f of a and f of b, it has to have a corresponding value somewhere in that interval, in this case from a to b. So you might say, oh, that sounds interesting, but what can we do with it? Well, there is one pretty interesting implication of this. By the way, here they're trying to show you how if the function is discontinuous, that would mean that there could be a k where this is not true. And that's what you're seeing here. So in other words, k is in between these two, and yet there's no c that corresponds to it. So anyway, here's where this might come in handy. What if we have a function that's continuous over the closed interval, but here's the key. They want this result will only work as long as you make sure that the two values f of a and f of b have different signs. Then, now remember, now often what we want to do is solve for equations in calculus. And so that means we're looking for the point where the function crosses the horizontal axis. So here, that point is clearly C. So as long as the two endpoints have different signs, based on the intermediate value theorem, we're guaranteed the existence of a solution C in this interval. Right? There's got to be a point in there somewhere between A and B, which has a value of 0. Okay. So that's one of the times when this theory can be very helpful. You may have a function, you're not sure if it has a solution over a given interval. Well, you can use this result to prove it. As long as the function is continuous and the f of A and f of B have negative different signs, that guarantees the existence of a solution in that interval. Because f of C, as you can see from the graph, equals 0. Okay, so that means we don't know what it is, but we know that it exists. Okay, so that's the best we can hope for. At least we know it's there. We just have to look for it, but at least we can prove that there is such a solution. So that's one of the nice applications of the intermediate value theorem. So here, oh, see, here's a specific example. So let's say we have a cubic function x cubed plus 2x minus 1. And we're looking at the interval 0, 1. Now, again, because this is a polynomial, it's going to be continuous everywhere. We don't have to worry about continuity. So what we'd like to know is there a solution in that interval? Now, of course, if we went ahead and solved for it, we wouldn't have to worry about such things, but sometimes it's not so clear cut. Is there a solution or not? And even then, there may be solutions, but they're not in this interval 0 to 1. So we need to evaluate this function at the two endpoints. Okay, so that's good. Our requirements are met. And so if we were to draw a graph of this, and they've already very kindly done that for us, it looks something like this. Let's see. So between 0 and 1, f of 1 is 2. What was that again? X cubed plus 2x minus 1. And here at 0, negative 1. Okay. All right. So as you can see very clearly that the solution is right here. It is definitely in that interval somewhere. Whatever it is, and we can call that C comma 0. All right. So now, of course, we still have to find it. And because it's a cubic equation, it's going to be a little challenging. Sometimes we can factor it out and reduce it to something simpler. But either that or, well, we have to try other techniques. Now, what's interesting is that I just actually saw a video where they said that we already are very familiar with the quadratic formula. It's very simple. It's very easy. You plug in the numbers, you get your solution. It turns out that there does exist a similar formula for cubic equations, but it's such a mess that almost nobody ever uses it. But it does exist, but it's like hardly worth it because it's so complicated. What a shame, because the quadratic formula is so helpful. All right. Let's see, what do they have for us here? A limit. Let's see what they want us to do. Sometimes, yeah, there we go. Sometimes it takes a while. All right, now clearly, as you can see, if you plug in 11 here, you're going to get 0/0. We can't have that. So direct substitution is not going to work here because 11 minus 11. Not good. So why don't we try this? First, let's rewrite it as minus x plus 11. And actually, let's try this. We can factor the denominator. Now, unfortunately, this numerator is 11 minus x. Let's rewrite it like this. So what we can do is rewrite this as negative. And now it's easier to see that we can reduce this equation or this expression. So these cancel out. And now we're good because the limit of we're done. Okay. So yeah, -1/22. So why don't we throw this into Symbolab and see what it looks like? So it's 11 minus x over x squared minus 121. Wow, what a mess. So now if you notice the point of interest, the 11 is right here. Let's zoom in on that. And there's a discontinuity there. Oh, God, it's so small you can hardly see it now. But yeah, there's a discontinuity, but because it's the same coming from both directions, the limit of this function is that as x approaches 11 is in fact equal to -1/22, although it's impossible to see it from here. It looks like 0, but it's because we're zoomed in so close. But it is -1/22. And then here, they want us to check out this function. Let's just quickly throw it into Symbolab. X over x squared minus 2x. So this actually has two different kinds of discontinuities. As you can see, it's got an asymptote, which is a non-removable discontinuity, and this single hole here, which is a removable discontinuity. So it has one of each. And that means, let's make sure it's a multiple choice. It's non-removable at 2, removable at 0. All right, that means it's A. That's right. Okay, great. All right. So now that was one word. So what's left? There's only one more section before we get into chapter 2. Now, in chapter 2, we're going to start differentiation. Now, this is one of the foundational topics in calculus. In much of the time when you're doing calculus, you'll be spending your time doing differentiation. And you'll see how it ties in with limits. The formal definition of derivative is based on limits. This is why they're doing it in this sequence. Limits have to come first because derivatives are defined in terms of limits. So we're going to spend quite a bit of time with differentiation. And we'll also see how it ties in with everything you learned in pre-calc. So it's a very important chapter. But first, we have one more section to go here. 1.5, the very last section in chapter 1 is this one, infinite limits. Sometimes our limits are infinite. It does happen. Okay, so we have to understand how that works. So you can see, well, all right, so actually, I guess we'll stop right here. We'll start this fresh at our next session. And what we're going to do is consider the notion of infinite limits. And then we can start our discussion about derivatives, which is really, that is going to prove to be maybe the most important topic in the entire course. I mean, really, if you think about what you're going to be doing with this material, a lot of it will come down to derivatives. So we'll have to save that for next time. I don't want to get your hopes up and then not do it, but it's like a cliffhanger. You'll have to wait till next time to find out what derivatives are all about. Okay. Anyway, so we'll stop right here, and then next time we'll wrap up section 1.5, and then we'll go on to derivatives. All right, so I'll see you then.